Hello everyone, myself Misha, Department of Electrical Engineering. Today we are going to learn about semiconducting materials. The semiconducting materials mainly used in the manufacturing device like integrated circuit, transistor, diode, etc. According to its conductivity, the material broadly classified into three types, that is conductor, semiconductor and insulator. Conductor, semiconductor and insulator. Conductor, let's define conductor. Conductor is a material through which the current can pass easily. The example of conductors are aluminum, copper, gold, silver, etc. So the conductivity of a material can be defined if the resistivity is low and the conductivity is high, then we can say it is a good conductor. If we take as an example of copper, then the conductivity of copper can be defined as 10 to the power 7 Siemens per meter, where Siemens per meter is the conductivity of the material. Next, insulator. Insulator defines a conductor through which the current doesn't pass is called as insulator. The example of insulators are rubber, wood, mica, paper, etc. If we take an example of dry wood, is the best example of insulator, then 10 to the power minus 14 Siemens per meter, and we can say it is the good insulator for the good insulator. Now let us discuss about semiconductor. The semiconductor means it is the partially flow of current or intends to flow the current through a material. If the current can pass partially means some of the current can pass, or we can say can stop the current. Then such type of material is called as the semiconducting materials. So semiconducting materials example are germanium, silicon, gallium, arsenic, etc. So the example of semiconducting metals are gallium, silicon, germanium, etc. are the example of semiconductor. The example of semiconducting materials are germanium, silicon, gallium, arsenic, etc. If we take an example of silicon, then the atomic structure of silicon is 14. That means the 14 number of proton and 14 number of electrons are present in the crystal structure. Let us consider in a cell. So this is the silicon structure, and this is K, L and M cells. So in the form of cell, the electrons are present in the 2n square formula. So what is 2n square formula? Let n equals to 1, then the formula for 2 into 1 square equal to 2, again 2 into 2 square equal to 8, 2 into 3 square equal to 9. So the electrons can be present in first orbit, that is 2, in the second orbit, that is 8, and in the third orbit of the last orbit it is 4. So you can see there are the 4 number of electrons present in the last orbit. So we can say the last or outermost orbit is present 4 number of electrons, then we can say it is a valence electron, or it can be a semiconducting material. So let us consider one more example. Germanium. The germanium atomic structure is 32. Atomic number is 32. So germanium, in the first orbit there will be 2 electrons. In the second orbit there will be 8, and in the third orbit there will be 18. Electrons, and in the last or outermost orbit you can find there are 4 electrons that are called the valence electrons. In the energy band diagram you can say for the conductor it is the conduction band, the layer called as it is the conduction band, valence band, and it is the conduction band, and where the valence electron and conduction band electrons are in overlap. So there is no need to give extra energy to move the electrons from valence band to conduction band. So here the energy gap is very negligible, that can be considered as 1 electron for the conductor. And in the case of semiconductor, the energy gap is little bit more than that of conductor. So this space is known as energy gap, where the valence band and the energy band is the gap between the energy band, and the space between the gap between the valence band and conduction band is 3 electron volt. If we apply up to 3 electron volt, then the electron from the valence band to conduction band moves. In case of insulator, the valence electron and the conduction electron in the band, there are much more gap, that is particle energy gap is 15 electron volt. So in case of insulator, there is no possibility, or there is minimum possibility to move the electron from the valence band to electron conduction band. So there is required a 15 electron volt is required to move the electron from valence band to conduction band. Next, in the semiconductor case, if we taken as the silicon, then we can say in the outermost orbit we can find the 4 valence electron which can be moved while the temperature is raised. So at the temperature is given 0 degree Kelvin, then the electrons are moved from here to another position. If the electrons move from one place to another position, then this space is a hole created. So the hole is created due to the excitation of heat, and the electrons move. So that in the case of semiconductor, there is 2 type of current flow, due to the electron flow and due to the holes. The semiconductor may be classified into 2 types, that is intrinsic semiconductor and extrinsic semiconductor. The intrinsic semiconductor and the extrinsic semiconductor. When a pure type of semiconductor is known as the intrinsic semiconductor, when some impurities are added to the pure semiconductor, then it is called extrinsic semiconductor. So in intrinsic semiconductor, the example of germanium and silicon. When a pure, some of impurities are added to a pure semiconductor like germanium and silicon semiconductor, then it forms a extrinsic semiconductor. So the process by which we add the impurities to the semiconductor or the pure semiconductor is known as doping. So by the doping process, we can add the impurity or we can add the different type of material to the pure semiconductor is known as the doping. By doping process, we can change the conductivity of a semiconducting metal. Again, extrinsic semiconductor is of two types. Here, extrinsic semiconductor are two types, that is called the P-type and N-type of semiconductor. So, in P-type semiconductor, the majority carrier is holes and the minority carrier is electron. In N-type semiconductor, the majority carrier is electron and the minority carrier is holes. Suppose in a conductor, we apply the voltage, then the current will automatically flow. Since the current flows in a conductor, there is some of electrons and holes are formation. At the time, the positive terminal is connected to the holes and the negative terminal are attracted towards the electrons. Then in P-type semiconductor, suppose in the silicon crystal, if we add some P-type, like P-type means pentavalent impurity, in trivalent impurity. And N-type means pentavalent impurity. So N-type means pentavalent impurities like aluminum, boron, etc. And pentavalent impurities are arsenic, phosphorus, etc. When aluminum is added to the pure conductor, then you can say you can find the 3 valence electrons can be found in the orbit and there is no electron can be found. So this space is required for one more electron to move from valence band to conduction band. So this is called the acceptor. This is called the acceptor. That means when pentavalent trivalent impurities are added to a pure semiconductor, similarly pentavalent impurities like arsenic, antimony and phosphorus. Pentavalent impurity, pentavalent means where the 5 number of electrons can be found like arsenic, antimony and phosphorus. Arsenic, antimony and phosphorus atoms are added to the pure crystal silicon crystal, then you can find, suppose phosphorus is added to the crystal of silicon atoms, then you can find there are 5 more electrons can be found in the outermost orbit. So the 4 electrons can be tried to move from this band to another band or it combines with another atoms. Now this is the free electrons is called as the donor atom, because one more atom is there to go for and join with another electrons. Suppose we are having a trivalent impurities, that is 3 electrons, and this place is space, this is 3 place, and another is 5 more electrons. So this atom will move to the space. Then this will, when the place will be, when the electron will be placed to the this 3 space, then this will be the, and this can say 4 valence electron, and here also will be a 4 electron, so that the semiconducting material will be flow from conduction valence band to conduction.